conveys this feeling of fragmented, broken, fractional, irregular.
It took a long time for us to emerge and start to look out at the other part of the physical observable universe, not as narrow studied little entities, the scientist who studies the flea on the back of the flea on the back of the flea, but rather being able suddenly to look out at the totality of nature and then say, my goodness me, we've got nothing to describe this with. Clouds are not made with straight edges. Trees are not circles. They're not triangles. They're something very, very different indeed. But there's a continual kind of a pattern that I can see as I look at the edge of a rising cumulus cloud, one of those very, very wrinkly, coruscated clouds that has such fine structure in it. And you say, but there's no lines or circles there. The wonderful discovery has been that there's an extension of classical geometry, Euclidean geometry, which is called fractal geometry.
Fractals are shapes which we are extraordinarily used to in, how to say, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You cannot put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away, you see very little, and the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed was arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, all kinds of putting together all these things and using them as bricks, if you will, of a new building, which is a new geometry, which is a geometry of shapes which are equally rough at all scales.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractals. And I'd like to show you how she does this. Now I'm going to generate a fractal before your very eyes. What you see here is what's called the seed, and it's an appropriate word in this case. Those two lines represent the first generation of the formation of a geometrical figure. And the computer has been told to continue growing these lines, but changing the direction every so often and at different distances. Now that's a very simple set of instructions, but look what happens after they've been carried out for, say, 10 generations. The tree I showed here, and it does look very much like a tree in nature, is symmetrical because the two branches at the beginning were the same length, off in the same direction. But if we change the length of one branch and change the direction, look what happens. In a way, this is a more realistic tree than the first one, because in nature you seldom have perfect symmetry. Much more elaborate structures can be created by very similar rules. I'd like to emphasize that all these shapes or objects, whatever you call them, although they look real, are generated entirely in the computer by following out a few simple instructions and repeating them over and over again. This is the way in which nature creates things.
It's exactly like the DNA in a butterfly's egg. Somehow that unravels and unrolls to form the extraordinary and beautiful pattern on a butterfly's wing with its myriads of colors and form. Somehow it's hidden in that seed, in the DNA, and not only that, but the wings themselves probably only occupy a relatively small part of the total DNA. They are, if you like, a little formula that is unraveled by the process of growth and deterministic following of rules to form this natural and beautiful thing.
Living creatures seem to be complicated structures produced from simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures is organic but pattern structure. Leaves on trees, ferns particularly, things like that, have the same feature that the Mandelbrot set has of you look at little pieces of them and they have lots and lots of detail. And in fact the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.
Once you develop a fractal geometer's eye, you can't help but see them everywhere. Every single thing you see is one way or another described by reference either to itself or to something else in the picture you see. It's as though you're staring at a vast dictionary, but the dictionary words are bits of pictures, and the references, the definitions of the words are made with other bits of pictures. And so you stare at one picture. I look out in the garden and at the trees, and I see this set of relationships between the picture and other bits of the picture. Those relationships are no more nor less than the assertion, from my point of view, that what I'm seeing is fractals everywhere.
The discovery of fractal geometry changes completely the kind of patterns we can look for in nature. And that is a really fundamental change to the sort of things mathematicians and scientists can do. And that's got to have a big effect.
Fractal geometry is already being applied throughout the physical sciences as a way of describing data in a new way. And the dream is that a fractal geometer can describe a cloud as simply as an architect can describe a house. He can use his intricate, repeatable formulas, simple formulas, to describe these unimaginably complex and beautiful shapes, and then communicate them from me to another scientist, to you. Here's not my straight line, build it straight, but here's my ragged formula, but it's very simple. Go build it wild like this. Can sort of think that they might even be the sort of semaphore of nature, of the physical world, of how it tells itself what it's supposed to be.
Let's go back to the Mandelbrot